The Moon orbits Earth at an average distance of more than 200,000 miles. It's a vast journey through space, far beyond the reach of most spacecraft that circle our planet today. For comparison, the International Space Station travels just 250 miles above Earth's surface. From that altitude, astronauts can see continents, oceans, and the thin blue atmosphere that protects life on our world. But the Moon lies nearly 1,000 times farther away. And for more than half a century, no human has traveled that far from Earth. The last time astronauts ventured into deep space was in 1972, during the Apollo 17 mission, the final chapter of humanity's first era of lunar exploration. Now, more than 50 years later, a new mission is preparing to take astronauts back beyond Earth's protective magnetic shield and into deep space once again. NASA's Artemis II mission will send 4 astronauts on a journey around the Moon, traveling farther from Earth than any humans have gone in generations. To make that journey possible, NASA built the most powerful rocket of the modern era, the Space Launch System. The Space Launch System, often called SLS, was designed for one purpose: to carry humans and heavy cargo far beyond Earth's orbit. For 3 decades, NASA's Space Shuttle carried astronauts to low Earth orbit. The shuttle built the International Space Station, launched satellites, and conducted hundreds of scientific missions. But it was never designed to travel to the Moon or beyond. When the shuttle program ended in 2011, NASA faced a new challenge. If humans were going to return to deep space, the agency would need a completely different kind of rocket. A rocket capable of lifting massive spacecraft, carrying astronauts safely across hundreds of thousands of miles, and supporting missions that could one day extend even farther, toward Mars. That rocket became the Space Launch System. SLS is the backbone of NASA's Artemis program, an ambitious effort to return humans to the Moon and establish a long-term presence there. Future missions aim to build lunar infrastructure, test technologies for deep space travel, and prepare for the next great step in human exploration. But developing a rocket powerful enough for these missions would normally take decades. So instead of starting entirely from scratch, NASA turned to something it already had: decades of proven engineering experience. Technology from earlier spacecraft programs would become the foundation of this new deep space rocket. Building a rocket powerful enough to send astronauts to the Moon is an enormous engineering challenge. Designing every system from the ground up could take decades of testing and development. So for the Space Launch System, NASA chose a different approach. Instead of starting entirely from scratch, engineers built upon technologies that had already proven themselves in flight. Many of the systems that power SLS trace their heritage back to the Space Shuttle program. The 4 engines at the base of the rocket, known as RS-25 engines, originally flew on shuttle missions, where they launched astronauts into orbit for more than 30 years. These engines were among the most advanced ever built, capable of operating under extreme temperatures and pressures while delivering extraordinary efficiency. Other parts of the rocket also draw from earlier programs. The massive solid rocket boosters mounted on the sides of SLS evolved from the boosters that powered the Space Shuttle. But with an important upgrade, an additional propellant segment that increases their thrust. The rocket's interim upper stage is derived from the Delta IV rocket, another vehicle with a long history of successful launches. By combining these proven technologies with modern engineering upgrades, NASA created a launch system capable of carrying humans far beyond Earth orbit once again. The result of this engineering effort is the Space Launch System, the most powerful rocket NASA has built since the era of the Apollo program. Standing more than 320 feet tall, SLS rises above the launch pad like a towering column of metal, fuel, and advanced technology. When fully fueled and ready for liftoff, the rocket weighs over 5 million pounds. At launch, its engines and boosters generate a combined thrust of more than 8 million pounds, greater than even the legendary Saturn V that once carried astronauts to the Moon. But the Space Launch System is more than just a single rocket. It was designed as a family of launch vehicles, with increasing capability over time. The first version, known as Block 1, is the configuration used for the early Artemis missions. It is capable of sending roughly 27 metric tons of cargo toward the Moon. Future versions will become even more powerful. The Block 1B upgrade will introduce a new exploration upper stage, allowing the rocket to carry both astronauts and large cargo together on deep space missions. And the most advanced version, known as Block 2, is expected to lift even heavier payloads, making it the most powerful rocket ever built. But the true scale of the Space Launch System becomes clear when we look at how this enormous vehicle is assembled. From its powerful engines to the spacecraft that sits at its tip, the rocket is made up of multiple systems stacked together into a single towering machine. The Space Launch System is not a single piece of hardware, but a carefully stacked collection of major systems, each designed to perform a specific role during launch and the journey beyond Earth. At the very top of the rocket sits the Orion spacecraft, the capsule that will carry astronauts into deep space. Attached above Orion is the Launch Abort System, a safety tower designed to pull the crew capsule away from the rocket if an emergency occurs during launch. Just below Orion is a structure known as the Orion Stage Adapter. This section connects the spacecraft to the upper stage of the rocket, and it also houses a series of small scientific satellites that can be deployed once the spacecraft is on its way to the Moon. Beneath that sits the rocket's upper stage, called the Interim Cryogenic Propulsion Stage, or ICPS. This stage provides the critical engine burn that pushes Orion out of Earth orbit and onto its trajectory toward the Moon. Below the upper stage is a large conical structure known as the Launch Vehicle Stage Adapter. This adapter connects the upper stage to the massive core stage of the rocket and helps distribute the enormous forces generated during launch. At the center of the vehicle is the core stage, the largest single element of the rocket. It holds the liquid hydrogen and liquid oxygen propellants that feed the 4 main engines at the base. And on either side of the core stage are the 2 enormous solid rocket boosters, which provide the majority of the rocket's thrust during liftoff. When stacked together, these components form a launch vehicle taller than a 30-story building, a machine designed to carry humans farther into space than any rocket has in generations. At the center of the Space Launch System is its largest and most critical component, the core stage. Standing more than 212 feet tall and measuring over 27 feet in diameter, the core stage forms the backbone of the entire rocket. It serves as both the main structural element and the primary fuel tank for the vehicle during the first phase of flight. Inside this massive structure are 2 cryogenic propellant tanks. One stores liquid hydrogen and the other stores liquid oxygen. Together, these super-cold fuels power the rocket's 4 main engines during ascent. In total, the core stage holds approximately 537,000 gallons of liquid hydrogen and nearly 200,000 gallons of liquid oxygen. These propellants are kept at extremely low temperatures so they remain in liquid form. During launch, the fuel flows from these enormous tanks down through the engine section at the base of the rocket, where it is burned by the RS-25 engines to produce the thrust needed to push the vehicle toward orbit. The core stage operates for about 8 minutes after liftoff. During that time, it accelerates the rocket to thousands of miles per hour, carrying the spacecraft high above Earth's atmosphere. Constructing a structure this large, capable of holding vast quantities of cryogenic fuel while enduring the intense forces of launch, required some of the largest manufacturing facilities ever used in rocket engineering. The core stage is built at NASA's Michoud Assembly Facility in New Orleans, where engineers assemble its enormous aluminum lithium tanks using advanced robotic welding systems. One of these tanks, the liquid hydrogen tank, is the largest hydrogen fuel tank ever built for a rocket. Once assembled, the stage is transported to NASA's Stennis Space Center for testing, before eventually being delivered to the launch site in Florida, ready to become the heart of a rocket capable of carrying humans back to deep space. At the base of the Space Launch System core stage sit 4 engines that convert enormous quantities of cryogenic fuel into the power required to lift the rocket off Earth. These are the RS-25 engines, among the most advanced liquid-fueled rocket engines ever built. Each engine burns a mixture of liquid hydrogen and liquid oxygen, producing roughly 418,000 pounds of thrust. Working together, The 4 engines generate more than 1.6 million pounds of thrust during launch. But these engines were not originally built for the Space Launch System. The RS-25 engines first flew on NASA's Space Shuttle, where they launched astronauts into orbit for more than 3 decades. During the shuttle era, these engines became known for their extraordinary performance and reliability, operating under extreme temperatures and pressures while delivering remarkable efficiency. For the Space Launch System, many of these engines were carefully refurbished after their shuttle flights and upgraded with new controllers and modern avionics. These upgrades allow the engines to operate at higher power levels than they did during the shuttle program, helping provide the thrust needed to launch the much heavier SLS rocket. The engines are mounted in a square configuration at the bottom of the core stage. Each engine can pivot or gimbal slightly during flight. By adjusting the direction of the engine thrust, the rocket's guidance computer can steer the vehicle and maintain its trajectory as it climbs toward space. While the 4 RS-25 engines provide immense power, they are only part of what lifts the Space Launch System off the ground. The majority of the rocket's thrust comes from 2 enormous solid rocket boosters attached to either side of the core stage. Each booster stands about 177 feet tall, nearly the height of a 17-story building, and together they generate more than 7 million pounds of thrust at liftoff. In fact, these boosters provide roughly 75% of the total thrust needed to launch the rocket from Earth. The boosters used on SLS are derived from the solid rocket boosters that powered the space shuttle for more than 30 years. But for the Artemis missions, engineers made an important modification. The shuttle boosters were built with 4 propellant segments. The SLS boosters add a 5th segment, increasing the amount of solid propellant inside and significantly boosting the rocket's overall thrust. Each booster burns through about 6 tons of propellant every second during the first phase of launch. For roughly 2 minutes after liftoff, the boosters and the core stage engines work together to accelerate the rocket through the thickest part of Earth's atmosphere. Once their fuel is exhausted, the boosters separate from the rocket and fall away from the vehicle, allowing the core stage to continue powering the spacecraft toward orbit. Unlike the boosters used during the Space Shuttle era, the SLS boosters are not recovered after flight. But during those first moments of launch, they deliver the immense burst of power needed to lift one of the largest rockets ever built away from Earth. Above the enormous core stage of the Space Launch System sits the rocket's upper stage, a system responsible for guiding the Orion spacecraft out of Earth orbit and onto its path toward the Moon. For the early Artemis missions, this role is performed by the Interim Cryogenic Propulsion Stage, often called the ICPS. The ICPS is derived from the upper stage used on the Delta IV rocket, a launch vehicle with a long record of successful missions. Like the core stage below it, the ICPS uses liquid hydrogen and liquid oxygen as propellants. At the heart of the stage is a highly efficient engine known as the RL-10. This engine performs several critical maneuvers during the mission. After the core stage separates from the rocket, the ICPS ignites to place the spacecraft into a stable orbit around Earth. Later, it performs another powerful burn that sends Orion on its trajectory toward the Moon. Above the upper stage sits the Orion stage adapter. This structure connects the ICPS to the Orion spacecraft while also serving another unique purpose. Inside the adapter are a series of small satellites known as CubeSats. Once Orion separates from the rocket and begins its journey toward the Moon, these CubeSats are released into space to perform a variety of scientific experiments. Some study radiation in deep space, while others test new technologies or observe the Moon and surrounding environment. Together, the upper stage, adapters, and spacecraft form what engineers call the integrated spacecraft and payload element, the section of the rocket that ultimately carries astronauts beyond Earth orbit. Once fully assembled, this entire system is stacked onto the core stage during the final stages of preparation inside NASA's Vehicle Assembly Building. Soon, the towering rocket is ready for the journey to the launch pad. Once the Space Launch System is fully assembled inside NASA's Vehicle Assembly Building, the rocket begins one of the most recognizable steps in the launch process: the slow journey to the launch pad. At Kennedy Space Center in Florida, the massive vehicle is transported to Launch Complex 39B by a machine known as the Crawler Transporter. This enormous tracked vehicle moves at a walking pace as it carries the rocket and its mobile launch platform along a specially prepared roadway. The journey covers nearly 4 miles from the Vehicle Assembly Building to the launch pad. From a distance, the crawler appears almost small beneath the towering rocket, but the machine itself weighs thousands of tons and was originally built to transport the Saturn V rockets during the Apollo program. Once the rocket arrives at the pad, engineers begin a series of final tests to ensure that every system is ready for launch. One of the most important of these tests is known as a wet dress rehearsal. During this rehearsal, the launch team practices the entire countdown sequence, including loading the rocket with its cryogenic propellants, liquid hydrogen and liquid oxygen. These fueling operations allow engineers to verify that the rocket, ground systems, and countdown procedures are functioning properly before an actual launch attempt. During preparations for the Artemis II mission, these rehearsals revealed several technical issues that required further attention, including a hydrogen leak at a fueling interface, adjustments to certain valves, and a helium flow anomaly within the upper stage. To address these issues, the rocket was temporarily rolled back to the Vehicle Assembly Building so engineers could complete the necessary repairs. Once those final adjustments are made and the rocket returns to the launch pad, the Space Launch System will stand ready for the moment it was built for: the launch that will send astronauts farther from Earth than any humans have traveled in more than half a century. When the countdown reaches 0 and the engines ignite, the Space Launch System begins a journey unlike any human spaceflight mission in more than 50 years. Moments after liftoff, the rocket climbs through Earth's atmosphere, powered by its core stage engines and solid rocket boosters. Within minutes, the boosters separate, and about 8 minutes after launch, the core stage completes its burn, leaving the upper stage to guide the Orion spacecraft into a temporary orbit around Earth. But this orbit is only the beginning. After 2 loops around our planet, the upper stage performs a maneuver known as the translunar injection burn, accelerating Orion to more than 25,000 miles per hour and sending the spacecraft on its path toward the Moon. As Orion travels outward, it begins to leave the protective bubble created by Earth's magnetic field, the magnetosphere. Most human space missions remain safely inside this region, shielded from much of the radiation carried by the solar wind. Artemis II will go beyond it. For the first time since the Apollo missions of the early 1970s, astronauts will travel outside Earth's magnetic shield and into the environment of deep space. After several days of travel, Orion will approach the Moon. But unlike the Apollo spacecraft, which orbited only about 70 miles above the lunar surface, Artemis II will fly much farther out. The spacecraft will pass the far side of the Moon at an altitude of roughly 3,000 to 9,000 miles. From this distant vantage point, the astronauts will see nearly the entire lunar disk at once before gravity guides Orion around the Moon and sends the spacecraft back toward Earth, completing a journey that will carry humans farther from our planet than anyone has traveled in more than half a century. With the Artemis program, humanity is taking its first steps back into deep space. Each launch, each mission, and each new discovery will expand our understanding of the universe and our place within it. Thank you for joining us on this journey through the engineering and ambition behind NASA's most powerful rocket. If you enjoyed exploring the future of spaceflight with us, be sure to subscribe and follow Wormhole to Cosmos for more documentaries that uncover the science and technology shaping our exploration of the universe. And remember, the universe is vast, mysterious, and full of wonders waiting to be explored. Stay curious, keep looking up, and until next time, keep your eyes on the stars.